In this example, we're looking at a steam power plant cycle. This is actually a Rankine cycle. And we're told that we have saturated water vapor entering the turbine at 12 megapascals. So this is coming in at state 1. And saturated liquid exits the condenser at a given pressure. That's over at state 3. We're told the net power output of the cycle. That's going to be the power coming out of the turbine. Just draw that W dot out. Minus the power going into the pump, W dot in. And we're told that the isentropic efficiencies of the turbine and the pump are 80%, and we're asked to find a number of things here. And then lastly, we're asked to draw a TS diagram for the cycle. So this is a Rankine cycle, and it's not ideal because we are given some isentropic efficiencies of the turbine and pump. We'll make use of that information a little bit later. But the general approach we'll take to find all of these various things is we'll apply the first law to different components along the way. So one of the things that we'll want to do if we're going to be applying the first law is we're going to want to find properties at each of these states. So let's get started on that. So state 1, this part is kind of tedious in the problem, but it's a necessary part. State 1, we're told that we're dealing with saturated water vapor at a given pressure. Okay, so we're told saturated vapor, the working fluid is water, and we're told that the pressure at P1 is 12 megapascals absolute. That's equivalent to 120 bar. So we can go to the saturated property tables for water and look up the corresponding temperature for that. That'll be 324.68 degrees Celsius. The specific enthalpy will be the specific enthalpy for the saturated vapor. That's 2685.4 kilojoules per kilogram. And we'll also write down the specific entropy. We'll use that specific entropy in addition to the isentropic efficiencies to figure out what H2 will be, what the specific enthalpy at state 2 will be. So S1 is SG1, which is 5.4939 kilojoules per kilogram Kelvin. I don't recall which table I used for this. These properties may come out of the back of your textbook, or they may be from the Excel table. It was a while ago that I worked through this problem, so I can't remember exactly which one I used. Okay, so that's state 1. Let's now focus on state 2. So for state 2, the way we'll find conditions there is that, well, first of all, one of the things we know about state 2 is we can figure it out from we can figure out the pressure here at state 2 because we know the exiting the condenser, the pressure is 0.012 megapascal, so that's at state 3 here. But we know that the pressure across a condenser is a constant. So we know that P2 will equal to P3, so that's one piece of information we know. So P2 equals P3, and that'll be 0.012 megapascals, which is 0.12 bar. So that's one piece of information we know. And if you recall the picture for just kind of a general TS diagram for a Rankine cycle, recall state 1 is right up here, right as a saturated vapor. Let me draw the isobar corresponding to that. So this is P1. Our state 2 was along a different isobar that's less than that. So P2 is less than P1. This is the 0.12 bar isobar. And recall that if we're at a saturated vapor up here at state 1, then state 2 will be a saturated liquid vapor mixture down here. Right, so that's our state 2 will have a slightly larger specific entropy than state 1. But it'll be a saturated liquid vapor mixture, so the temperature corresponding to state 2 will be the saturation temperature at that pressure. So we can go back to the tables to find the saturation temperature for that. That comes out to be 48.66 degrees Celsius. And since we're dealing with a mixture, I need to find the, I'm going to have to find a quality. So let me just write down some properties that I'm going to use here. So the saturated liquid specific enthalpy at state 2 will be 203.73 kilojoules per kilogram. The saturated vapor specific enthalpy will be 2588.9 kilojoules per kilogram. We can do the same sort of thing for the specific entropy. So we're just looking these values up from the table, and we're going to use them to calculate a quality for state 2 ultimately. Okay, I think I've got all those. Actually, you know what? I just rewrote the same number. I apologize, I was looking at the wrong number. Let me rewrite that one. The SG2 is 8.10048. All right. So I know that I'm going to be dealing with the saturated liquid vapor mixture, but I still don't know exactly where I am there. So what, where I am for state 2. So what I'm going to do is I'm given the isentropic efficiency of the turbine, and from that information I can figure out state 2s. Mark it right there. There's state 2s. That has the same specific entropy as state 1, right? Because it's for an isentropic process, the specific entropy remains constant. And if I can find the conditions for the isentropic case, then I can use the isentropic efficiency to find the actual case. Okay, so that's where I'm headed to. Let me just write that down for you. So the isentropic efficiency for the turbine, recall, is the actual work that you get out divided by the work you would get out if it was isentropic. And if you worked out the first law on the turbine for those for the actual workout, it would be H1 minus H2, and for the isentropic case, it would be H1 minus H2s. So if I can do some rearranging here to solve for H2, I'll get the following. H2 is equal to H1 minus the isentropic efficiency of H1 minus H2s. So I already know H1, I figured that out. I know the isentropic efficiency, that's given. So if I can find H2s, then I can find H2. And I should be able to find H2s because I know that S2s is equal to S1, which is the 5.4939 kilojoules per kilogram Kelvin. So given the specific entropy, as well as knowing the pressure and temperature, I can find the quality. I have enough information to determine the rest of the states, so I can find the quality at state 2s. You'll see that the 5.49 is between the saturated liquid and saturated vapor values, so it will have some quality. And if I can find the quality from that, then I can use that quality to calculate H2s. And then once I have H2s, I can find H2. So there are a number of steps involved. So let's first find the quality at state 2s. That'll just be S2s minus SF2s all over SG2s minus SF2s. Okay, so we have all the numbers given above to find that. And when we solve for that, that comes out to be, well, I guess I didn't actually solve for that. What I did is I just said that same quality will be the same quality used to find the specific enthalpy. So let me just write that down. So whatever quality I get from the specific entropy calculation. So I could plug in numbers for this to get that quality, and that'll be the same quality as for the specific enthalpy. I know the HF and HG values, that those are given right up here. So I could substitute all that in to solve for H2S. Okay, so if I do that, it's just tedious. Hopefully you understand the concept. That comes out to be 1748.33 kilojoules per kilogram. Now that I have the specific enthalpy for the isentropic case, I can go back up to my expression that came from the isentropic efficiency, plug this H2S right up into there. I already calculated H1 above. I know the isentropic efficiency, so I can then calculate H2. And when I do that, that comes out to be 1937.41 kilojoules per kilogram. All right, so now I know my H2 value. While I'm there, I could also calculate the quality at state 2 and also the specific entropy at state 2. Might as well do that while we're here. Notice, let me go back up to the picture. Notice that state 2 and state 2s are along the same isobar. So they'll have the same pressure. They'll also have the same temperature. You can see that right here. Right, so T2 and T2s are the same. Right, so I know all the information I need at that particular state. It'll be the same temperature as what we have here. And you can see that this specific enthalpy is between the saturated liquid and saturated vapor specific enthalpy. So we still are in a saturated liquid vapor mixture state. Right? So we'll still have some quality. We can calculate that. And that quality, when you work out the numbers, this one I did work out, it's 0.7269, so about a 73% quality. And then I can also calculate S2 using that quality. And when you plug those numbers in, that comes out to be 6.07521 kilojoules per kilogram Kelvin. The reason I did this is I just wanted to show that the S2 is a little bit larger than S2S. You can see up there, as expected, right? So the S2 right up here is a little bit larger than the S1 or S2S. Okay, so now we have our specific enthalpy for state 1 and for state 2. That'll be useful for when we apply the first law to a control volume surrounding the turbine. So we can use that information to find the power coming out. All right, let's continue on and find properties at state 3 and state 4. So we're told at state 3 that we have a saturated liquid exiting the condenser, and we're told the pressure. So state 3 is going to be right at this point there. Right, so we're moving now from state 2 over to state 3. Saturated liquid and the given pressure. So we can use that information to find the rest of the conditions at state 3. Saturated liquid. Pressure at 3 is the same as pressure 2, same as pressure 2s. And that is the 0.12 bar. So we can use the property tables for that. And you'll see that it'll be the same temperature, right? And we'll have all of these quantities are still the same. But it's same temperature because you can see as we come across from 2 to 3, it's still the same temperature. So T3 is the same as those, T2 and T2s. And then here is S3. Okay, so let's write everything else out there. So H3 will be 203.73 kilojoules per kilogram. That's just the saturated liquid vapor value. So if you come back up here, it's just this value. And then our specific entropy for state 3 will be that value. And then T3 was still 48.66 degrees C. All right. Let me just double check. 6856. Yeah, okay. All right, so that gives us state 3. Now we're moving on to state 4, our last state. Well, actually, it's not quite the last state. We're going to use the state 4s. So for state 4, we're going to do just like what we did for state 2. We know that going from 3 to 4, we're passing through the pump, and we're given the isentropic efficiency of the pump. It's 80%. So we're going to make use of that information to find out what's happening at state 4. So just as a reminder, state 3, what we do is we move isentropically upward to state 4s, which would be right there. So that's the ideal case. For the actual case, the entropy will increase. So state 4s has the same specific entropy as state 3. State 4 will be at a slightly larger specific entropy. It'll have S4, which will be larger than S3 because the pump is not 100% efficient. And if you look at the temperatures corresponding to these, you can see T4s will be a little bit less than T4. And both, of course, are less than T1 up there. And then from 4 to 1, we'll follow that isobar back over. Okay, so we've drawn out we've actually done part B here, drawing our TS diagram. That's right over here. It's a little small and crammed in, but you generally get the idea. Okay, so let's continue on to find what's happening at state 4. So we're going to find out what's happening at state 4s and then use the pump's isentropic efficiency. So P4 and P4s will be the same as P1. We're on the same isobar. As we move through the boiler, the pressure remains constant. So from 4s, and P1, they're all the same pressure, and that's the 120 bar pressure. Okay. And we also know S4s is equal to S3. So that's 0.68576 kilojoules per kilogram Kelvin. So we should be able to find then what the conditions are for state 4s, and then from that information we could find what's happening at state 4 using the pump isentropic efficiency. So let me just write down that pump isentropic efficiency. So here's the isentropic efficiency for the pump. This will be the power going in isentropic. That'll be less than the power going in the actual case. And if you write out what you get from the first law on those, it'll be H4s minus H3 for the isentropic case. The actual case will be H4 minus H3. So you could rearrange that equation to get H4 in terms of H3 and H4s in the isentropic efficiency. All right, so we need to find H4s first. All right, so we know that, let me go back up to the picture again. We know state 4 and state 4s are compressed liquids. Okay, so we can use, we can try to find our conditions for compressed liquid. We can make use of our compressed liquid approximations and such to find the conditions at state 4s. So one thing that I'll do is, let me just write down, there are different ways you can do this, but let me just show you one way. In the next example, I'll do it a different way. Let's just start with the TDS equation. in terms of specific enthalpy. If you go back to our notes, this is what the TDS equation looks like, right? And if for an isentropic process, which is what we're saying in going from 3 to 4s, the ds would be 0. And so we're left with dH is equal to v dp, right? So our going from state 3 to state 4s, our dH would be h4s minus h3. And then our specific volume, if we're dealing with a compressed liquid, I'm going to assume for this particular case that I'm dealing with that the specific volume doesn't change very much, that it's essentially an incompressible substance. So then the specific volume would just be the specific volume at 3, for example. And then the pressure difference would be P4S minus P3, which we know. Right, so we could solve then, so the specific volume at state 3, we could look that up from our property tables, and if you do that, that comes out to be 0.001012 cubic meters per kilogram. We know our pressures, we know H3, so we can solve for H4S. That comes out to be 215.86 kilojoules per kilogram. And then from that, we can now get our H4 from our expression up here involving isentropic efficiency for the pump. So that comes out to be 218.89 kilojoules per kilogram. All right, so this is one way to find the conditions at state 4s. There's, like I said, there's a different way we can do it using the compressed liquid approximations. I'll save that for a different example. They're approximations, so they're not going to give you exactly the same answers, but they'll be very close to one another. Okay, we now have all of our values for the specific enthalpies. Let me go back up to the problem statement. We're asked to find the flow rate of the water in kilograms per hour. So what we can do for that is, if you look at the problem statement, we're given the net power output of the cycle. So that means that we're given the W dot out minus the W dot in. So that's, let me write that down. W dot out net is W dot out minus W dot in. And we're given that that value is, let me just go back to look at the number. The number is 122 megawatts, right? So if I apply the first law to find W dot out, so that's the first law applied to the turbine. I'm not going to write it all out here because this example is already long enough, but we've done this many times. You should be able to show that W dot out is M dot times, it'll be, go back up to the picture for the turbine, it'll be H1 minus H2. And then we can do the same thing for the W dot in. So this is first law for the pump. That should be M dot times H4 minus H3. So we can substitute these back in right up here and then solve for M dot. Okay, so it's going to be the same M dot. That comes from conservation of mass. It'll be the same M dot throughout the whole cycle. So let me plug those in up here. So this will be H1 you know what, I won't write that down. You get the idea. So we can solve now for M dot when you plug in our values for the for all the specific enthalpies that we just found moments ago. And if you work that out, that comes out to be almost 600 times 10 to the 3 kilograms per hour when you work out the numbers. Okay, I think you get the idea. So it's an application of just the first law applied to the pump and the turbine. Okay, so that's our first part here, mass flow rate. Now we're asked to find the heat transfer into the boiler. So what that will be the first law applied to the boiler here. We know the specific enthalpies at states 1 and states 4, so we should be able to find the Q dot in into the boiler. And we can do the same thing for part 3 for the condenser. It'll be the first law applied to the condenser there to find the Q dot out, because we know the specific enthalpies at 2 and 3. So let's do those. I'm not going to write out the entire first law just for the sake of time here. So if we apply the first law to that control volume surrounding the boiler and work it all out, we'll get Q dot in is m dot times H1 minus H4. And you can plug in the numbers for that, and that'll come out to be 411 megawatts. And we can do the first law to the condenser. If you want the details for applying the first law, I'll have them in the solutions, the PDF of the solutions, so you can take a look at that. So Q dot out will be H2 minus H3. And that number comes out to be 289 megawatts. Okay, so these are all straightforward applications of the first law, which you've done many times. The very last thing we're asked to find in the problem is the thermal efficiency of the power plant cycle. So the way we can find that is it'll be the net work out of the whole cycle divided by the heat that comes into the cycle. So it's like putting a control volume around the whole cycle, sort of like this. And if I redrew that picture, it would look like this. There would be some hot reservoir that puts the Q dot in to our system. This dashed blue line is the same dashed blue line over on the right hand side. Then we have our Q dot out going into our cold reservoir, and then this is our net power out. Right, so this dashed blue line right here is the same as this dashed blue line. Okay. So our thermal efficiency for the power plant cycle will be the net power out divided by the rate of heat transfer coming in. And we just worked out those numbers, right? So we can substitute those in, and what you'll get is it will come out to be 0.297 or 29.7%. And that's our thermal efficiency. The very last bit of the problem is the TS diagram, but we've done that early on, so that's this picture over here on the right hand side. So we've got our actual path from 1 to 2 and our actual path from 3 to 4 where the specific entropies increase. We've got our ideal case that I just drew as a dashed line because we don't actually take those paths. They're just, I put them there as part of our, just to show what happens for the isentropic efficiency case. And then I highlighted with arrows the actual path that we're taking. All right, I think that does it for this example. So we'll end there.